So we talked about this metric topology. We defined this metric topology, and if you have a space with metric topology, people sometimes call it a metric space as well, where you can define a notion of distance. So now what I want to talk about is something called a continuous maps. Continuous maps. Let X and Y, both of them are topological spaces. They don't have to be same. They can be different topological spaces, or so to say, two different sets endowed with two different topologies. So topological spaces. Then if I define a map from X to Y, and it's called continuous if the inverse image of an open set in Y is an open set in X. This is the definition of a continuous map between two topological spaces. And I think Mancres has this as an exercise. I did it a long time ago. I don't recall it right now. Is that from this definition of these continuous maps, you can derive the epsilon delta definition of continuity that you see in your usual calculus course. I think Mancres has it as an exercise, if I recall correctly. But for us, for this course, we don't need that. We don't have to do all those proofs and stuff. So what is a continuous map? Well, if you go from one topological space to another, then inverse image of an open set in Y, that means you're going from this topological X space to topological space Y through some map. Then the inverse image of open sets, what does the inverse image do? Well, it maps your elements from, or so to say, something from your topological space Y to topological space X. So the open sets in Y under the mapping F inverse will also be open in X. Okay, that's the definition of a continuous map. That's the definition of continuous map. And now one of the most important definitions that you will ever see if you pursue physics, and that is the definition of neighborhoods and Hausdroff spaces. And Hausdroff. So at first, let's take a look at the definition of a neighborhood. So let's say tau gives a topology to some set X. N is a neighborhood of point. N is a neighborhood of a point X which belongs to the set capital X if N is a subset of X and N contains some and at least one open set UI to which X, small x, belongs. which means small x belongs to ui. Note that this definition might seem a bit absurd at first because you are used to, you know, draw or understand neighborhood in terms of points, right? But when you extend that definition in terms of sets, you can no longer deal with points anymore. So you have to talk in terms of sets, right? And these small x, they are just elements of set. What are those elements? We don't know. They might be points, they might be cows, dogs, whatever. So if you have a set like this x, and there is some element of capital X which is denoted with small x, what this definition is telling you is that, first of all, if you want to define a neighborhood of this element x, then if you call that neighborhood capital N, first of all, it should be a subset of x. Okay, so let's say this is my subset N, and then it tells you that this subset N, it's a subset of x, and N contains some or at least one open set to which x belongs. That means if this is your N, which is a subset of x, and the small x also belongs to N, at the same time this N will have to carry some open set which is denoted with ui. So let's say this is your open set ui. Then you can call this N as a neighborhood of the element small x in some set capital X. If it didn't contain any open sets which contained x, your small x set element, then you couldn't call it a neighborhood. Do you understand what I'm trying to say?
So N itself is not necessarily an open set.
Is N an open set? No, not necessarily.
It just needs to
It can-
contain an open set.
Yeah, let's say you want to, yeah, that's what it does, right? I mean, that's what the definition tells you. But yeah, there can be open neighborhoods. If your N is open, then it's called a open neighborhood. Let me, write that as a comment, so that comment N does not have to be open necessarily, but if it's open, then we call it then we call it an open neighborhood. Okay, Saif, anything else? I think
No.
you were able to say something. Okay, anyone else?
So the N can have empty set in it and still be a neighborhood, right?
No. Null set doesn't contain anything.
If it's an empty set, there is no x that is contained in it.
Yeah, just look at this condition. Like, to understand this kind of long definitions, for what I do is that I read the lines. Like, if you look at it once, it seems very absurd, but you see on each of these lines that I wrote over here, there are some specific, very, very, very specific conditions, right? First of all, you have to put your element inside N. N has to be a subset of X, and N also has to carry an open set that is containing small x, the set element inside itself. So your null set, it doesn't contain anything, so it cannot be.
Oh.
Not all the neighborhoods, not all the things you can define will qualify as a neighborhood.
What about if the inner small x is partially in the
No.
N? Okay.
It has to. So what do you mean by this symbol? It has to be inside, and there is no partial thing.
Okay.
Okay, so let's now define the Hausdroff space. Hausdroff. A topological space let's write it as x tau, is a Hausdroff space. Hausdroff space if for an arbitrary pair of distinct points x comma, let's say x prime, these two are distinct points which both of them belong to capital X, there always exists neighborhoods ux of x and ux prime of x prime such that ux intersected with ux prime is null. So what do I mean by this? Let's take our set X. I have two distinct points, or so to say two distinct elements, and I can have these two neighborhoods like this. This is one of the neighborhoods ux, and let's say this is another neighborhood ux prime. If your topological space is a Hausdroff space, then their intersection is null. That means they doesn't intersect. And what is so good about this thing? And or you may ask, okay, why did you call it important? Well, if you don't have a Hausdorff space, the first thing that happens is that you cannot define a unique limit. So I think you can pick up from what I said is that if you cannot define a unique limit, any type of physics you want to do, it just goes to dogs. So any type of thing that we do, we actually do it on Hausdorff space. And if you have done a course on GR or you plan to do a course on GR is defined over these Hausdorff spaces, and that's why it's a very important thing. But how do you prove it? Well, you need concepts of limit points and all those stuffs to do this. Again, if you are interested, you have to first read about limit points, and from there you can actually prove that if they intersected somehow, then there wouldn't exist a unique limit. And just go to Manpress if you want to read it. If you don't want to read it, that's fine.
What is a unique limit?
What did you do in your Math 110 course? You calculated limits, right?
Yes.
How did you define limit?
A point or a point.
No. That's not what I'm saying. I'm saying you have some function. You're trying to calculate some limit, right? So what did you do? You went from the left side of the point. You went from the right side of yeah. And if they didn't match, you said, oh, there is no limit, right? Like
Yes.
this, right? The limit doesn't exist. That's what I'm talking about. Like, do you get my point? What I'm trying to say?
Sure.
Yeah.
লিমিট পয়েন্ট তো হচ্ছে মানে একটা সেটের কোন মানে
No, I'm not saying limit points are equals to limit. I'm saying that to prove that there is no unique limit, to prove that you need to have this concept of limit points, which I'm not covering because this is not a topology course. We need some, definitions of it. So that's why I'm introducing these stuffs. But limit point is an entirely different thing. It's not your, if Rafid's question was what are limit points, then limit points are entirely different things than what we do in Math 110 or Math 105.
No, sorry, it was only unique limit.
Oh, unique limit. Yeah. Okay. Then that's related. That's the thing you do in your calculus, right? That is the most easiest example.
So the Hausdroff space don't have any unique limit.
I think you just said the opposite of what I mentioned over here. If you don't have a Hausdorff space, you don't get a unique limit. Okay. It has to be Hausdorff. It has to be. Otherwise, none of the calculations you would do in your, engineers or physicists, they would do it. From my point of view, that wouldn't make any sense. Because you are saying, oh, the limit of this function at this point is 5. I'm saying, no, it's 50. And both of us are correct. That's absurd.
So for the Hausdorff space, unique limit has to exist.
Hausdorff property or Hausdorff, if you have a
I
space,
guess it's the other way around. যে
yeah,
unique limit exist করতে Hausdorff space হতে হবে।
yeah, if you have a unique limit, that means it is a Hausdorff space. Or if you say, what do I have to do to get a unique limit? You have to work in a Hausdorff space. Otherwise, you won't get a unique limit ever.
Oh, got it.
Okay.